The last type of aromatic substitution that I'd like to talk about is the opposite of electrophilic aromatic substitution, and now we have nucleophilic aromatic substitution. So nucleophile is a word you're very familiar with from Organic 1, negatively charged substance, substitutes into things. Cool, got it. So attacks carbons, negatively charged, that's a nucleophile. If you don't know that, watch some more Go 1 videos again. That way you'll get more familiar with it. This will come easier to you. So nucleophilic aromatic substitution is pretty straightforward. Converts a leaving group, commonly a halogen. Notice we have a halogen, into a hydroxyl or an OH. Requires a very strong electron withdrawing group, or EWG, in the ortho or para position. It's almost always a nitro group. It's almost always an O2. So when you're drawing the products for this, what's going to happen is you're just going to literally draw the same thing, but instead of the halogen, go for an OH. Bottom example, it's the same situation as the top example. Same thing. Done. Awesome. Or you could draw it the other way if you don't like drawing things close to other text. Either way, I just flipped it over, no big deal. Cool, so let's talk about the mechanism, and we're actually going to use this example right here. So I have it on the next page. We're going to redraw the product just for practice. Sheesh. There we go. Not a lot better, but it works. So, obviously OH. So this OH from NaOH, the OH minus is what kind of does the work. So, let's get right into the mechanism here. So we'll put our arrow, we'll put our OH minus. We're going to draw an arrow, just classic Orgo 1 style, lone pair the OH minus to the carbon. Now this is it's kind of a series of arrows, so you're going to do a bunch of stuff, and then you're just going to undo everything you just did, and you're going to pop the bromine off. Okay, so the first thing is the first step, second step. Ready? So here you go. So this bonds to here, well then this carbon would have 1, 2, 3, 4, 5 bonds. That doesn't happen. So this double bond goes here. That's the second arrow. This double bond comes here. So the nitrogen is now double bonded, and then you're going to bust the double bond to this oxygen. Ready, set, go. Done. So 4 arrows. Now we're going to draw a really freakishly awkward intermediate that we don't isolate because it's crazy. So we're going to start at the top. We're going to put our OH and our Br, right? So now the only double bonds we have in this ring are here and here, so they're parallel to each other. Double bond, double bond. Remember, the nitrogen is double bonded. Both oxygens are now single bonded. Positive charge on the nitrogen. So, remember when I said you're going to do a bunch of stuff, and then you're going to undo everything you just did and pop off the bromine. That's exactly what you're going to do. Now, technically, okay, you could take a lone pair from either one of these oxygens and make a double bond. I'm just going to put the same one back on that I just took off. So arrow from a lone pair of the oxygen to the nitrogen-oxygen bonds. You're going to end up with that N double bond O, okay, on one side. Second thing you're going to do is this double bond to nitrogen is going to break. It's going to go back into the benzene ring. Next thing you're going to do is you're going to move this double bond one space over. Last thing you're going to do is you're going to pop off your bromine. So you're going to do a lot of stuff, and you're going to undo everything you just did, and you're going to get rid of the leaving group. And so, when we draw our product, we now have the OH on top, we have our aromatic ring, and we have our nitro group down on the bottom. And you can write this the same way. You can just go aromatic ring, OH on the top, NO2 on the bottom. Do make sure that you're showing that it's bonded to the nitrogen. That is helpful. So that is one method of nucleophilic aromatic substitution. And the second method of nucleophilic aromatic substitution is the Benzine method. So you remember from your nomenclature from Organic Chem 1, hopping between the classes is not helping my vocab. Okay, that the YNE means we have a carbon-carbon triple bond. So instead of a strong activating group, or a strong electron withdrawing group, we have now really intense conditions. So we have 350C, but the reality of the reaction is still the same. Replacing that leaving group with hydroxyl. So the mechanism for this reaction, and we're going to draw in really quick the hydrogen right there. That's going to be helpful. So we're only really going to talk about the OH here. So instead of doing anything directly to the carbon that the Br is bonded to, the OH is going to deprotonate this hydrogen. Here's where your benzyne comes from. Bromine pops off. Now you get to draw benzyne, which is super fun. It's no different than benzene. You just make one of them a triple bond. It's not a big change. And I know that looks a little bit funky as a triple bond, but bear with me, that's just what it is. And then we have another equivalent of OH minus, which will come over and attack this carbon, pops this bond back off. So now we have OH, we have an extra lone pair on this carbon. How will we ever get rid of that? Oh yeah, we're using H3O+. So it will come in and be protonated by H3O+. And we get our product, which I will write a nicer OH on the top for you. So we get the same product from the Benzine method. So that was nucleophilic aromatic substitution, both through the Benzine method and through the regular method, which is right here. Again, I hope that was a lot more, I guess, it lended itself a lot better to just a quick understanding. So break a bunch of bonds, reform the bonds, keep the OH, lose the bromine, keep the OH, lose the bromine, and we're good. So I will see you in videos about carbonyl chemistry.